Hello everyone. Alkenes are molecules that contain a carbon-carbon double bond in their structure. In this session, we will talk about some of the properties of alkenes, and later we will talk about the preparation and their chemical reactions. So as I told you, alkenes are molecules that are characterized by the presence of a carbon-carbon double bond in their structure, and that is why they are known as unsaturated hydrocarbons. The term unsaturated means that we can add a molecule across this carbon-carbon double bond to convert these alkenes into saturated hydrocarbons. Because of the unsaturation present in the alkenes, the general formula is CnH2n. So if you have n number of carbon atoms in the structure, it will have double the number of hydrogens in the molecule. Carbon-carbon double bond is present between sp2 hybridized carbon atoms, and as you know that sp2 hybridized carbon atoms are considered to be slightly more electronegative than the sp3 hybridized carbon atom, and that is the reason that these alkenes have a slight dipole moment. It's not very large, but it still is there. Just like alkanes, as we have discussed earlier, the boiling points and melting points of alkenes also increase with their molecular weight. So the low molecular weight alkenes are usually gaseous or in liquid form, and the high molecular weight molecules may be in solid phase as well. Let's talk about the stability of alkenes. As I told you that alkenes have carbon-carbon double bond in their structure, and a double bond has a sigma bond as well as a pi bond present in it. That makes the bond slightly stronger than a single covalent bond. But still, these molecules have variable stability. Now, the carbon-carbon double bond, as I told you earlier, is between sp2 hybridized carbon atoms, and because they are slightly more electronegative than the sp3 hybridized carbon atoms, they attract electron density from the groups that are attached to it. And if there are any electron donating groups attached on the carbon-carbon double bond, that will increase the stability of the alkenes. In other words, it will increase the stability of the carbon-carbon double bond. As this double bond is attracting in nature, so any electron donating substituent or electron releasing substituent will increase the electron density on the carbon-carbon double bond, and that will increase the stability of the alkenes. So more the substitution, more will be the stability. And because of this, we can classify these tetrasubstituted, trisubstituted, disubstituted, or monosubstituted, or unsubstituted alkenes according to their stabilities. So as we said earlier, that the number of substituents present on the carbon-carbon double bond is directly related to the stability of these alkenes. So more the number of substituents or electron donating substituents, more will be the stability. Here in these examples, you see that this carbon-carbon double bond is substituted with alkyl groups. Methyl group is an alkyl group, and alkyl groups, you know, they are weakly electron donating in nature. So if you have more alkyl groups, the stability will increase, because so as the number of alkyl groups increases on these carbon-carbon double bonds, the stability of the molecule increases. So a tetrasubstituted alkene or tetraalkylated alkene will be more stable as compared to a tri-substituted or a trialkylated alkene, which will be more stable than a dialkylated alkene, which will be more stable than a monoalkylated alkene, and which will be more stable than a simple ethylene, which is unsubstituted. Another important fact about the stability of alkenes is that sometimes these bulkier groups may be on the same side or on opposite side of the carbon-carbon double bond. So when these bulkier groups are on the same side of the carbon-carbon double bond, they are closer to each other in space, and that brings about some steric hindrance or steric repulsion between them. To avoid that steric hindrance or steric repulsion, they would tend to be on opposite sides of the carbon-carbon double bond. So when alkenes have bulkier groups trans to each other, they are more stable than the cis isomer, which means that if the bulkier groups are on opposite sides, trans is a terminology that is used for groups on opposite sides of the double bond, and cis is the terminology used for groups on the same side of the carbon-carbon double bond. So if the groups are on opposite side, then they will be more stable because there will be less steric hindrance between the groups. So as you can see here, the two isomers, the trans isomer and the cis isomer of this alkene, you see that this carbon-carbon double bond is substituted with alkyl groups. In this case, they are on opposite sides of the carbon-carbon double bond, and in this case, they are on the same side of the carbon-carbon double bond. And that is why this isomer is known as the trans isomer, while this is the cis isomer of this 2-butene. Because of the steric hindrance or repulsion between these methyl groups, which are on the same side of the carbon-carbon double bond in the cis isomer will be less stable as compared to the trans isomer. The cis isomer will be less stable as compared to the trans isomer. Or on the other hand, we can say that the trans isomer is more stable than the cis isomer. So basically, there are two factors which affect the stability of the alkenes: the number of substituents or the number of electron donating substituents on the carbon-carbon double bond, and the orientation of these bulkier groups on the carbon-carbon double bond. So this is how alkenes are characterized or classified according to their stabilities. We will talk about the preparation of alkenes in the next section. Thank you so much.